Hello AP Physics 2 students, we are starting our optics unit today, and in order to do so, we have to review a little bit about waves from AP Physics 1. I'm going to make this fast, but obviously if you have questions, let me know, and then in this video we'll move on to the new stuff, the optics stuff. So just some reminders. A wave is nature's way of carrying energy. It's a disturbance of some sort. We have mechanical waves, such as sound, which do require a medium to travel through. We won't really be talking about those since this unit is about optics. We are talking about non-mechanical waves, so they do not require a medium to travel through. The main example are electromagnetic waves, so we'll be talking about infrared, ultraviolet, radio, X-ray, gamma, visible light. Can't remember if I forgot any, but we will be talking about all of those. We also can categorize waves as transverse or longitudinal. For optics, we're looking at transverse waves, which are light waves. So our disturbance is perpendicular to the direction the wave is moving. So you can see on the left that we have our disturbance, which is that red dot that is moving up and down. The wave is moving to the right. The disturbance is perpendicular to the direction the wave is moving. So that is a characteristic of transverse waves. Once we start talking about light waves more, we will talk about how really we have a magnetic field and an electric field that are perpendicular to each other. They both look like transverse waves, so you really have two fields propagating, but we'll get to that later. We also have our basic wave vocabulary. Again, not really looking at the longitudinal waves, but we have amplitude, which is our maximum distance from equilibrium. We have wavelength, which is our horizontal distance from crest to crest or trough to trough, essentially one cycle. We call our maxima crests our minima troughs. We have period, which is the number of seconds for one cycle, and frequency, which is the inverse of that, which is how many cycles are occurring per second. That all should be reviewed from last year or from chemistry. We also have our wave equation, which I know you've seen before. We will be using it. It says that the wavelength of a wave is equal to its speed divided by its frequency. We will be using c instead of v since we are talking about light. Okay, so let's start some actual optics. We'll be looking at chapter 24 from our textbook. So you can see here that we have something on the left that's creating an electromagnetic wave. And the purpose of this is I just want to show you right off the bat that a light wave is really an electric field and a magnetic field that are perpendicular to each other. So that magnetic field in blue would really be coming out of the screen and going into the screen. It's perpendicular to that electric field. And those two fields propagate perpendicularly to each other, creating two transverse waves that together are what we call an electromagnetic wave. So, like I just said, electromagnetic waves are transverse. They are non-mechanical. They don't require a medium. They can travel through empty space. So if we had something that was creating an electric field or a magnetic field, in general, those fields die off pretty quickly as you move away from them. They don't have very far-reaching effects in terms of distance, but an electromagnetic wave can move large distances. So that is because you have this changing magnetic field that produces an electric field, and then that electric field is changing, and then you have a magnetic field that's created, and that just continues back and forth for very, very large distances. We get light from the sun, that's an electromagnetic wave, many coming off of the sun, and that's able to travel very far to reach us. So this has also to do with electromagnetic induction, which we talked about last unit. In general, one way to get an electromagnetic wave is to have a charge that is accelerating. So all light waves move at the speed of light through a vacuum at 3 times 10 to the 8th meters per second. Later in this optics unit, we will talk about how the speed of light can change if the light is going through a different medium. So maybe it's going from water to air or something like that. But in a vacuum, the speed of light is 3 times 10 to the 8th meters per second. We can just use the symbol lowercase c for that. And the frequency of an electromagnetic wave can be determined by the oscillation frequency of whatever charge created it. So we don't get into the nitty-gritty detail right now about this. In our modern physics unit, we will, but the properties of the actual accelerating charge do affect what kind of electromagnetic wave is created. Some applications, a ton of applications, but here are some. So antennas on cars, you have a radio in your car probably. So either the electric or the magnetic field of the incoming light wave force the electrons in your car antenna or the wire loop to oscillate at a resonant frequency that matches that incoming wave, and then that can be converted into information, sound waves, all of that. So we did talk about resonance last year when we did waves, how something vibrating can force something else to vibrate at that same frequency. That's what's happening with radio and television reception. Cochlear implants, if you haven't watched those videos of babies getting their cochlear implants turned on for the first time and being able to hear, so moving. But those cochlear implants use radio waves to help people who are hard of hearing hear. And then also another medical application, wireless capsule endoscopy. That is a capsule that you can swallow, and then it uses radio waves to broadcast images of the GI tract, which is a far less invasive method than the alternative. Let's get into this electromagnetic spectrum and talk about each of the different types. So again, all of these electromagnetic waves move at the speed of light in a vacuum. And this spectrum ranges from 10 to the 4th hertz to 10 to the 24th hertz. And often these different types are referred to by their frequency. To start, we have radio waves. Lower frequency radio waves are usually created by electrical oscillator circuits, kind of what I talked about before. Higher frequency radio waves are also called microwaves. So you might see on the spectrum, microwaves doesn't have its own category. It's really a high frequency radio wave. Infrared radiation has to do with the vibration and rotation of molecules. A lot of people think of heat waves as infrared. There's no such thing as an actual heat wave, but some animals can actually see part of, like, into the infrared part of the spectrum. I think some snakes and fish and frogs. So some animals at night can detect living things using their infrared vision, which does have to do with heat. Visible light is, we call it that because that is the light that we see. This is emitted when an object's temperature is hot enough to excite electrons, which we'll talk more about in our modern physics unit. But if an electron is excited enough to jump from one level to another, it emits a photon of a certain frequency that corresponds to a type of color that we see. So visible light is pretty much right in the middle there. You can see that red light has lower frequencies, and then our violet light has higher frequencies. So then we have ultraviolet. So UV rays, we don't get too much into how they are created, but we all know that we use sunscreen to protect from UV radiation because it is damaging to human DNA. X-rays are caused by the sudden deceleration of high-speed electrons. We obviously have utilized X-rays in the medical field for a long time in order to take images of our bones. We also have gamma rays, which come from nuclear decay, which we will talk about in our modern physics unit, which are on the highest end in terms of frequencies on the electromagnetic spectrum. A little bit more about visible light. There's the range for frequencies if you need that. Usually for visible light, or commonly, it is described in terms of wavelength. So 1 nanometer, which is 10 to the negative 9th meters, is equal to 1 angstrom. That's essentially an obsolete unit, but you may see that. The AP test probably wouldn't use that, but just in case you ever need to know. The human brain recognizes light of different wavelengths or different frequencies as different colors. So the longest wavelength we see is about 750 nanometers, and then the shortest wavelength would be violet. Another application of electromagnetic radiation or light waves are microwaves, which most of us have probably used before. Let's say you put your food into the microwave. What happens is that the electric field of the microwaves that are being emitted inside of that microwave causes the water molecules in your food to spin. And if something is starting to spin, it is heating up essentially. So the energy from the microwaves that's going into spinning those water molecules and breaking down bonds between the molecules is transferred into the internal energy, which we talked about in thermodynamics, and your food heats up. Obviously, we also have the greenhouse effect, which is when infrared radiation from the sun is reflected off of the CO2 and water in the atmosphere. And then you have Earth's surface, which is heated, which is also radiating infrared radiation, and then that's trapped by the atmosphere. So you have this cycle of warming. Let's talk about polarization and some equations. So the speed of light c is essentially a proportionality constant between electric field and magnetic field. So if you're wondering what's the mathematical relationship between them, electric field is equal to the speed of light multiplied by magnetic field. The intensity of an electromagnetic wave, the symbol for that is capital S, and that is equal to the total power of that wave divided by the surface area, which is essentially then energy divided by time times area. The little equations at the bottom here, I don't recall using them very frequently for AP Physics 2, but they are available. Maybe we'll use them in an example this week. We shall see. Polarization, maybe you've had sunglasses that are polarized before, and if you're looking at a computer screen, for example, then you're wearing the sunglasses and you tilt your head 90 degrees, like you can't read the screen anymore. It looks like no light is coming off of that. Your glasses are polarized. They're essentially only letting light through that matches their orientation. So if something is linearly polarized, that means the vibrations always occur in only one direction. So in our picture here, you have this rope, that's the example, but we'll be talking about this for light. You have this rope. The rope itself is vibrating up and down. So it's able to go through this slit here because it's vibrating vertically and the slit is vertical. If we had a material and we had a horizontal opening, that wave would not be able to travel through the slit there. So we essentially just blocked that wave or that piece of information from entering. So unpolarized light is essentially what it sounds like. It's essentially emanating in all directions. It doesn't have only one direction it's going. That's this bottom picture here. It goes in all directions. It's random. Polarized light does have a single direction and it's traveling whatever way it's traveling, but it's already been restricted essentially. So the types of problems you're going to see, you need to know a couple pieces of vocab. So we can polarize unpolarized light. So let's say we start with some unpolarized light of intensity capital S. And if you're wondering what is intensity, it has to do obviously with power, which means it has to do with brightness. So you could think about how a very intense light would be very, very bright. That's good enough for now. So we have unpolarized light. It's going in all directions. It's moving to the right. And then it hits some sort of polarizing material. And the polarizing material has something called a transmission axis. And that's essentially, you could think of like the slit or the opening that only lets light that aligns with that transmission axis through. Everything else is blocked. So you have your unpolarized light, it goes through the polarizing material, and in the end, you only have light that matches that transmission axis. And what's always going to be true is that when the unpolarized light goes through the first polarizing material, the resulting light has an intensity of 1/2 the original unpolarized light's intensity. So you could have a system of these polarizers. So after you first polarize the light, then you can change its intensity and its direction. So we have our unpolarized light. It goes through something we call a polarizer. So that will be the first material it goes through. So then that lets the electric field that is vertical here go through. And then we have that light go through another polarizer. The second one is always called the analyzer though. And that now is going to only let light at this angle go through. And then maybe you have a photocell or something there. So you're using these polarizing materials in order to get the intensity and orientation of light exactly how you want it so that you can take a picture, do whatever you're trying to do. Then we have, lastly, Meyers Law, which says that the average intensity of the light leaving the analyzer is equal to the intensity of the light entering the analyzer times the cosine squared of theta, where theta is the angle between the transmission axes of the polarizer and the analyzer. So if that angle is 90 degrees, no light is transmitted. So going back to this picture, this means that we have our polarizer, which is vertical, and then we shifted that transmission axis there on the analyzer some angle theta. So if we were to rotate that so that it's 90 degrees compared to this transmission axis, no light would come through. Our intensity would be 0. And cosine of 90 is 0, so that makes sense. We will work on problems this week. Let me know if you have any questions, and that's it.